Okay, let's continue from where we left last time. So we've been going through a very quick fire review of systems and their properties, and we also focused on LTI systems. All of this is review for you because what happens in discrete time is a close parallel of what was happening in continuous time. And we focused on convolution, which is a very important aspect of LTI systems. And since an arbitrary signal can be expressed as a linear combination of scaled and delayed impulses, if you know the impulse response, you can find the response to an arbitrary input, and the output in such cases is given by the convolution of the input and the impulse response. And these are some of the exercises in continuous time that you need to be comfortable with. In particular, convolution of a causal sequence and an anti-causal sequence, you need to be able to, when you are doing algebraic calculation, you should be able to fix the limits and get the output for all values of shifts. So that is very important. Okay, so let us continue with this. If there are two sequences x of n and h of n which are of finite duration, then if their lengths are p and q, then the length of the convolution of these two sequences is easily determined, and without loss of generality you can assume p is greater than or equal to q. As h of n slides into x of n and remain within x of n, then p samples of the output are generated. So that is easy to see. And as h of n starts to come out of x of n, the output samples get generated till there is overlap, and the overlap lasts for q minus 1 samples, and therefore the total length is p plus q minus 1, right. And you get p plus q minus 1 because when the overlap ceases, one shift means a shift by one sample. So this is the difference between continuous time and discrete time. When the overlap ceases, as far as continuous time is concerned, just when the overlap ceases, the difference is just 1 point, and 1 point does not contribute to the length as far as continuous time signals are concerned. Therefore, if the duration of one pulse is t1 and the duration of the other pulse is t2, the overall duration in the continuous time case is t1 plus t2. Whereas in the discrete time case, it is not p plus q, but it is p plus q minus 1, because when you cease to overlap, difference is one sample. Now let us look at properties of convolution that you must already be familiar with. Convolution is commutative. So x convolved with y is the same as y convolved with x, and this is easily seen. All you need to do is you need to make a change of variable L equals n minus k, and if you did that just a couple of steps, you will be able to see that x convolved with y is the same as y convolved with x. So this is commutative. The next property that we want to see is associativity of convolution. So x convolved with y convolved with z is the same as x convolved with y convolved with z, and this is similar to the property in continuous time. And one way of seeing this is, if you convolve in time, you multiply in the transform domain, and multiplication is associative, and hence associativity of convolution can easily be seen by looking at the corresponding behavior in the transform domain. Now let us examine this a little more. So let us take x of n to be a power n, y of n is delta of n minus a times delta of n minus 1, Z of n is a power n u of n. So, these are the three sequences. Now, let us find out what x of n convolved with y of n is. So, this is nothing but a power n convolved with delta of n minus a times delta of n minus 1, and this is what? Okay, I think you need to push pen on paper rather than staring at the screen. So, this of course a power n convolved with delta of n is a power n minus a times a power n convolved with delta of n minus 1 is a power n minus 1. So, this is indeed a power n minus a power n, and the answer is 0. Now, x of n convolved with y of n. Now, we want to convolve this with z of n. So, this is indeed 0, which is the result of the first convolution, convolved with a power n u of n, and this of course is 0. Now, let us do the other convolution. So, we want y of n convolved with z of n. So, this is delta of n minus a times delta of n minus 1 convolved with a power n u of n. So, this is nothing but a power n u of n minus a times a power n minus 1 u of n minus 1. Okay. So, this is a power n times u of n minus u of n minus 1. U of n minus u of n minus 1 is delta of n, and a power n times delta n is delta n itself, because this picks out the sample at n equals 0, correct? So, now let us convolve x of n with the result of y of n convolved with z of n. X of n of course is a power n convolved with delta of n. So, this answer should be a power n, right. Therefore, a power n equals 0. Convolution is after all associative, right. Either a power n equal to 0 is true, or convolution is not associative, right. Yes. Say that again. So, a power n, a is indeed a constant. So, why is that a problem? No, no. So, what is it in this step that fails based on whatever objection you are raising? No. So, you said A being a constant is the problem, correct? So, where is it that is causing these steps to fail? Uh-huh. X of n minus n naught, yeah. Why? Why that won't apply? No, why is it that thing won't apply? That surely applies. Right? Unless I am not getting exactly what you are trying to point out. Um, Here we are talking only with properties of convolution. That convolution happens to be something that LTI systems satisfies. That's a different reason. So, why do you want to bring LTI systems here? This is purely a property of convolution. If someone didn't know LTI systems, he or she can still grapple with this particular example and then see something is not quite right. Okay, so you've been told convolution is associative. What you probably have not been told is that convolution is associative under certain conditions. All right. So, convolution is associative provided x of n, y of n and z of n belong to L1. L1 is the space of all absolutely summable sequences. So, L1 is the set of all sequences such that n going from minus infinity to plus infinity mod x of n is less than infinity. So, this is the space of absolutely summable sequences. Only if all the three sequences under consideration belong to this class, only then we can make the conclusion that convolution is associative. Right here, we have come up with an example where associativity is not valid, and the reason is this condition is violated. So, which sequence violates not belonging to L1? X of n. And z of n when mod a is greater than or equal to 1. So, when mod a is greater than or equal to 1, z of n does not belong to L1. Even when mod a is strictly less than 1, for that particular case x of n is not an L1 sequence. Therefore, when you are told that convolution is associative, implicitly in that statement is the assumption that all these three sequences belong to the space of L1. So, here is an example where that condition fails. The proof that okay, so that will take us outside the scope of this course. All right, Handbook of Fourier Theorems, Ciampini. Take a look at that book. I think it's Cambridge University Press. So, all the theorems that you study in both CTFT and DTFT, more rigor you will find in math books. So, the above holds provided that each of these three sequences belongs to the space of L1, and L1 is the class of absolutely summable sequences. So, if the sequences do not belong to L1, then associativity will fail. So, this is exactly the sequence that I worked out the details of just now. So, as we saw, each of these individual convolutions exists, there are no problems, but associativity does not hold. And proof of associativity is very simple in the transform domain. And it is simple in the transform domain because the transform you assume it exists, and a power n, which is the everlasting exponential, clearly does not have a transform. The only case where it does possess a transform is when a equals when oh yeah, very good, when a is e power j omega, then transform exists, the transform is impulsive. But anyway, these sequences require special treatment. So, whatever Fourier transforms that you have learned so far, it is without rigor. So, if you study Fourier transforms from the maths people, they will talk about the space of L1, cap L1 and cap L2, L1 functions and L2 functions, which are the class of absolutely integrable functions and the class of square integrable functions, absolutely square integrable functions. So, they divide the Fourier transform into these two subsections and study them more rigorously, right. So, as far as we are concerned, transform always exists, we do not care, right. We will leave the question of existence to those people. So, this is the counterpart to the continuous time signals. Again, we assume associativity provided these belong to the space of L1. So, this is the space of absolutely integrable functions, and here is an example where associativity will fail in the continuous time case. So, you can verify that each of these individual convolutions is well defined, the answer will exist, but associativity will not hold because it violates the requirement for associativity to be valid. Again, assuming the transform of each of these functions exists, the proof is very simple in the transform domain because multiplication is associative. Associativity of multiplication follows from multiplication is associative, of course. I mean, so assume for real numbers, right. So, it follows from, it is an axiom, right, one of the axioms that you assume for real numbers, all right. So, that famous book Calculus by Spivak, if you are interested, take a look at Spivak Calculus, amazing book. So, the first chapter talks about these axioms, and then distributivity, x convolved with y plus z is x convolved with y plus x convolved with z, and this of course follows from the distributivity of multiplication over addition. For real numbers, this follows, for real and complex numbers, based on that this convolution property is established very easily. CT convolution is also distributive. Now, this associativity and this distributivity property of convolution is just not an idle mathematical curiosity or property that follows. It really plays a very important role in practical applications. It plays a role in practical applications in that it helps us to break down complex systems into lower order subsystems. By complex systems we mean systems with high order, and you can break down such high order systems into combinations of lower order systems, and in practice typically we will implement lower order systems in terms of first and second order. There is no advantage of doing this when the precision is infinite, but in all practical cases the precision is finite. Whenever you are going to implement a system, you will be requiring say multiplier elements, and those multiplier elements cannot be of infinite precision. In discrete time systems, what you will do is these multiplier coefficients will have finite number of bits. When you have finite number of bits, you are introducing quantization error. When there is quantization error, then if you have a very high order system, if you want the quantized system's behavior to be not too different from the ideal infinite precision system, then you have to expend a large number of bits. Whereas if you break it down into smaller subsystems, the precision needed can be reduced, the number of bits needed can be reduced. So this is where this theoretical property is indeed very much used in practice, because lower order systems, it can be shown that they are less affected by quantization. And we carry out two kinds of decompositions. One is parallel decomposition. In parallel decomposition, the property that is used is distributivity, we will see that in a minute, and the other decomposition is cascade decomposition. And here two properties are used, both associativity and commutativity. These two properties are used. All right. So if you have a certain real number, typically when you are implementing it on a machine, we use binary representation, and when you are using binary representation, then you need to expend a certain number of bits, and if the number that you want to represent requires an infinite number of binary digits, you do not have infinite number of digits to expend. So you have to represent that number by a finite number of bits. So this means you are truncating the representation. So this is quantization, that is your actual real number having infinite precision. When it is represented as a sequence of binary digits, if the representation for exact representation is infinite, which is not possible, if you truncate there, right there you introduce quantization. All right. And even if a number can be represented in a finite number of bits, if that representation requires a large number of bits, suppose if it requires 100 bits to represent it exactly, you do not have 100 bits in practice, right. So typically if you want to guess what would be the number of bits that are used in practice? Say that again. Yeah, 16 is commonly used number of bits for representing numbers, and now because hardware is becoming cheaper, you can afford to spend more bits. For example, now for sound, typically what is the number of bits that are used to represent sound samples? What you do is, if it is an analog waveform, you sample and then you represent it as binary numbers, and the number of bits used for sound these days, any guesses? (24 bits). These days 24 bits is the standard for representing sound. So that I hope answers the question of what precision and quantization they mean. Okay, so in practice, higher order systems are typically broken down into first and second order systems, and this is where we come up with parallel and cascade decomposition, and these properties of convolution are indeed used here. So let us look at parallel decomposition first. Suppose you have h of n, if it is represented as h1 plus h2, so this is the higher order system. So this is broken down into h1 plus h2, so that x of n convolved with h can be represented as x of n convolved with h in turn is h1 plus h2, and then we use distributivity and get y1 and y2 as follows. So in terms of block diagram, you have this original system as given here, it is broken into these two subsystems and you get y of n. So again, to reiterate, you do not get any advantage out of this when the precision is infinite, but under finite precision these things help. So when you want to implement digital filters, we do what is called parallel decomposition. So we have a transfer function, we break it down into partial fraction expansion, and each of these terms is a smaller subsystem, and each of these subsystems is implemented like this, and then we add them up to get the final output. And each of these subsystems can afford to use a lower number of bits in terms of coefficients. And the next is cascade decomposition. Suppose h of n is h1 star h2, then you can replace h1 by h1 convolved with h2, and then you can interchange. So where there you use commutativity, and then again you are using associativity here. So what this tells you is order of interconnections does not matter. Again, if you have a high order system h of n and you have broken it down into h1 and h2, there are under certain conditions where you want to interchange the order. Again, when you do a course on digital filters, you will realize for certain noise criterion, noise spectrum criterion, it would make sense to order the systems in a certain way, and in a exactly opposite ordering would be what would be needed for some other criterion. So all of these things are used in practice. So this again parallels what you have learnt in continuous time. So if you have h of s, you can break it down into h1 of s times h2 of s, and then again exactly the same kind of ideas apply there. There is one difference between cascading of subsystems in continuous time versus discrete time. Again, this must be known to you or must have been pointed out to you. So in continuous time, if you had a system like this, R and R, so the overall gain is half, and if you cascade two such systems, right, if you just cascade it right away, the overall gain will be, no, here is a system with gain half, here is another system that is gain of half. So if you cascade these two systems, what do you expect the overall gain to be? Okay, this is an easy answer. It will be 1 by, so 1 by 4 is what you expect, right? What is the assumption under which the overall gain is 1 by 4? So this is, let us call this as h1 of s, this is h2 of s, right, and the overall system h of s is H1 of S times H2 of S. If you expect the gain to be 1 over 4, what is the assumption here? So here, right? Yeah, so now if you cascade these two, you expect the gain to be 1 over 4, but you can just connect these two and you can find out what is VO by VI. You will find that the answer to be 1 over 5. And the reason is so it won't be 1 over 4, it will actually be 1 over 5. It's very easy to see. So has this not been pointed out in networks and systems? Uh-huh. Okay, okay, very good. Yeah, so what you are assuming here is there is no, what's the term that's used for? No, no. So when you connect this, there should be no loading, right? So when you connect this, the individual currents that are flowing here are not the same when you connect them. When you connect this second circuit to the first one, the second circuit loads the first circuit. So the circuit, these individual systems are no longer the same, right? So the condition under which this is true is you need to connect these two by a voltage follower. So you need to connect these two by a voltage follower so that there is no loading, so that each of these systems, they are not changed when you connect them. So when you say you have, I have H1 of S and H2 of S, when you say I connect them and then the overall system transfer function is indeed H1 times H2, the implicit assumption is loading. And when it comes to continuous time systems, you need to worry about whether loading is there or not. If loading is there, this multiplication of transfer function is not valid. So when you assume the transfer functions are indeed multiplicative, the implicit assumption is no loading. When it comes to discrete time, no such issues are present, because here we are talking about implementation on a computer. So we are going to, these are all algorithms that are implemented on a computer. So there is no question of loading in the discrete time case. So we can assume that if I have H1 of n followed by H2 of n, in the transform domain, the corresponding transform will be the Z transform. It will be H1 of Z times H2 of Z, all right. And the concept of loading does not apply to discrete time systems. And these are some of the counterparts of convolution exercises that you should be familiar with. Again, you should be able to do the algebraic manipulation so that you get the correct answer. Again, because in the continuous time case the integration limits are minus infinity to plus infinity, and the discrete time case you have summation from minus infinity to plus infinity, you need to worry about these things existing. You need to worry about convergence of these things. Now let us focus on the LTI system and impulse response. So an LTI system is completely characterized by its impulse response. If you know the impulse response of an LTI system, you know everything about the LTI system. And the impulse response is actually a signal, all right, whereas the system is a system and everything is by a signal, and that signal is special, it is the impulse response. And conditions on the system can be restated as conditions on the signal. We will see examples of this. By the way, when you evaluate the impulse response of a system, what is it that you are assuming about the system when you are measuring the impulse response? This applies both continuous time as well as discrete time. So, based on your knowledge of continuous time system and the impulse response concept that you have learned, what is it that you assume about the system when you are, yeah, input is the impulse, so that is fine. Anything else? What is there anything that the system should be satisfying for you to, okay, yeah, LTI system, because only for such systems will the impulse response completely characterize the system. What is it that you are assuming about the system when you say impulse response? Say you have continuous time case, you have an RLC circuit. What is it about the system you are assuming when you talk about the impulse response of a given RLC circuit? Very good. No initial conditions, right. Similarly, for a discrete time system also, we are assuming all initial conditions are 0. Why is it that this is needed? If this is not satisfied, the impulse response won't be unique, right. So, now coming back to some of the conditions on the system being translated as conditions on the impulse response. One of the most important things is causality. So, if the system is causal, then h of n must be 0 for n less than 0. This is because the impulse is applied at n equal to 0. The system is causal, which means it cannot anticipate the impulse being applied, and hence it cannot produce a response before the impulse is applied. Therefore, the response necessarily has to begin at n equal to 0 and onwards. Therefore, for a causal system, the impulse response is always 0 for n less than 0. So, condition on the system is now translated to a condition on the impulse response. So, for continuous time systems, h of t is 0 for t less than 0. Similarly, for stability, the condition can be expressed as a condition on the impulse response, and we assume that the input is bounded, and this condition can be translated to a condition on the impulse response. This is no different from what you might have seen in continuous time case. So, we want y of n to be bounded, and if you try to bound the output, then you see that the absolute value of the sum is always less than or equal to sum of the absolute values, and so this is always less than or equal to bx. You can always bound this, upper bound it by the bound on the input, and you get this. And if you want this to be finite, this leads to the condition that this has to be absolutely summable. Only if this is true is the system bibostable. Therefore, condition on the system, namely bounded input must produce bounded output, is translated as a condition on the impulse response, namely it being absolutely summable. Counterpart of this in the continuous time case is impulse response must be absolutely integrable. And here is an example that we have already seen. So, we saw that the running sum is not a bibostable, because if you applied a step, the output is a ramp which is not bounded, right. The impulse response of such a system is nothing but u of n, because if you compute the running sum of the impulse, it is nothing but the unit step, and clearly the unit step is not absolutely summable. So, this example that we saw in terms of a bounded input u of n producing a ramp as the output, and therefore that is not bounded, is also seen in terms of the impulse response not being absolutely summable. In this case, the impulse response is U of n, right. Therefore, this system is not bibostable.